All right, so we're gonna do problem with trees. Let me go ahead and paste that here. Let me go ahead and comment it out while you read this through.
Sure. Okay, so just to make sure that I understand, I'm given a large tree T, and then I'll be given a smaller binary tree S, and I just want to find out if it's the same, which means that from some starting node, every left and right pointer matches up in T to what's within S.
That is correct.
So thinking about how I would end up doing this, let's try and go through an example. So the easiest tree is probably just something like, so it's a binary tree, not a binary search tree, right? So there's no ordering constraints.
It's a binary tree, correct.
Okay. So let's just say I have, say, 4, 2, 1, 3, even though this would fit, if I put it a 5, it would be a BST. Let's just say this is 1. That's my T subtree, and I have 2, 1, 3 as S. What I could start to do is, as a naive approach, just keep traversing through all of the left and right nodes, starting from the root until I find a node that matches the root of S, right? And then from there, just continue the traversal. This ends up taking, I want to say n squared time, because you could have the case that it almost matches in a lot of places, and you just revisit. So n squared wouldn't be a good bound. Let's say s squared time, right?
Sorry, what was that? S square?
Yeah, that's not right either. It should be s times t, where s is the size of the T tree, and then S is T is the size of the T tree, and then S is the size of the S tree. Because from each node, you may end up having to go and traverse up to S length, right?
Okay.
Though that's a worst case. Is there anything you would really do to improve on that? I guess one thing you could say is you can keep track of what nodes are visited, so that if it turns out no, okay, that wouldn't help. I was gonna say that maybe you had 2 2s, right? Or you had a 2 in here, and during your first traversal of the 2 on line 10, you would end up getting to the 2 on line 12, right? And you would say that it's already visited, but there's no reason that this next 2 on line 12 can't be the start of the root of your new tree, right?
Mm-hmm. Fair enough. Okay, so if we assume the elements are unique, what would be the worst case complexity of the tree?
If the elements are unique, in that case, you would just have to go through, I guess, every node once. So T.
And T is the size of the subtree, or
of the larger tree, right?
Okay, so the size of the larger tree.
Yeah, because you'd end up having to probably visit every node, right? In the case that there is no subtree at all that fits, you would end up doing a traversal of the entire thing.
All right, sounds good to me. And is that the best case in the first case scenario where the elements could be repeated?
Is that the best case? I'd say that's
the best. Mm-hmm.
Yeah, that definitely sounds like it would be the best case there, right?
Yep.
Because that means you're not going to make the separate call to search. So
exactly.
Given that, is it okay if I code it out?
Yeah, that's good.
So graph is subtree larger, smaller. Cool. So just as an edge case, we can say that if root is or larger is none and smaller is none, does this count as being true? Is none a subtree of none? So an empty tree. To me, that seems like that'd be true, but I just wanted to
Sorry,
get
what
the
was the question
definition from
again?
you. Is an empty tree a subtree of an empty tree? To me, that seems like it'd be true.
Let's assume true. Yeah.
Okay. Sure. So that was just like a boundary case, but I guess I can come back to thinking about boundary cases instead. I'll just continue with the main logic, where what I say I'm going to do is go through and traverse at every node. The simplest thing to do is to write this out recursively, so that if it turns out that I can start at this position, I'll make a separate call. Otherwise, I just recurse on left and right. Really, I would say return start or the real logic is mainly the matching portion, where I would just keep going through all the values of larger, smaller, and their respective subtrees. This is where I can just include that logic from before, where the empty trees should match themselves. False if larger is not none. Right. So I think this ends up being the entire set of logic that I would need, except that I'm missing the base case for the actual isSubtree function. So just to summarize, what I've done is I go through, and given larger and smaller, I just check from some point if there's a match. What I'll check first of all is that I don't have the one of the base cases matching, which is that if it turns out that they're both none, then obviously I'd return at that point, and I know that nope, I have a typo here on line 26. I know that if they're both none, then it is a subtree. If one of them is none and the other one is not, then I shouldn't return that it's a valid subtree, because I think actually that's not true, because I said when smaller is none, but larger is not none, that should still be the same case, right, as when they're both none. So this would still be true. Yeah.
So as long as it's a subtree, we need to return a true.
Yeah. So when larger is some value but smaller is none, then yeah, we would return true instead of false. But if it turns out that our larger, we're finished traversing, and our smaller, we still have items left, then this can't be a subtree, right? So we return false.
Sounds good to
and
me.
Because this will end up short-circuiting, even though we have these recursive calls on line 28 where we check for the larger left and larger right matching with the smaller left and right, if their initial values don't match up, then we're just going to return false immediately, right? This is only really making the recursive calls if the root matches to begin with.
Okay.
Right. So for each level, we'd want to say that we either found a starting from the node that we have right now, except this should be with larger, smaller, or it turns out that the start of the subtree is on larger's left or on its right. The is subtree function, though, doesn't have an actual terminating case, so you'd actually need to have these the same thing with larger and smaller between line 21 and 26.
Okay.
Do we need to include all of the cases? Let's think about that. I want to say yes, because you can have the exact same things happen later on, right? Where it turns out that, yeah, one of them is none, but the other one isn't. Let's just call this function def base smaller. No, I can't reuse this. It's probably just easiest to copy and paste again.
That's fine.
Yeah, so this should probably work out. Is it okay if I try and print out some test cases?
Yeah.
Okay. So I'll need a separate tree node class for this.
So what are we trying to do here?
Which part?
43.
43. Oh, sorry. I thought I called match there. It was supposed to just be if it turns out that we found the start, then we would return. Right, so let's just set it up. Cool. So let's just copy the tree node that I had from earlier.
Sure.
Two is going to end up being a tree node with 2 with 1 and 3 as the two sides. And then we'll have Subtree on 4 and 2. This should return true. Cool. So that seems to work out. And we know that it's not actually comparing the nodes themselves, it's only looking at the value. So it's fine to reuse our objects here. Covering some of the other cases, we'd want to make sure that when they're both empty, you would get true. When it turns out that the larger tree is empty, but the smaller tree is not empty, you would want to get false. So make sure that that works. And it's also the case where one of them, the smaller tree is empty, but the larger tree is not, you'd want that to return true. Right. But this really only ends up covering the code path that we have between line 25 and 30, right? For the cases where something might be none. The thing the other code paths you'd want to test are the lines between 34 and 39. And I think that our first test case actually covers most of that, just because we would never, stop recursing on the match function unless those worked out. yeah, I guess just reasoning through it, I'll go ahead and say that this is my solution.
Okay. So let's say, right? So which one is the subtree? 1, 2. Okay. And that's only one node. Is that right?
Yeah. So it's the same tree as that we're aiming for what's between line 8 and 12.
Okay. So 4 is the 4 to 1 to 3, right?
Yep.
Okay. So 4 is 4 to 1, 2. Okay. And 4 to 1. And then 2 should be 2. Okay, got you. 1, 3. You mean 2, 3. Okay, that's fine. And this is, which is the subtree is 2, which is 2, 1, 3. Okay. All right. So,
I was going to say the alternative test was also include the one where it doesn't match and they're not both empty. What I actually had written down where I had the 2, 2, 3 on lines 10 to 12. Yeah.
Okay. So you did this, right?
No. That wouldn't make any sense. I can make another test case for that. If anything. Yeah, I can write that one out. So it ends up being, what is it? I have something that goes from 2 to 3. Yeah, so instead it would be that 2 is equal to a tree node that points to 2 extra, to be a tree node that just has 2. So it would have 2 going to 2 extra, and then 3 as the right. And then 4 is going to end up equaling a tree node that goes to 4 and has 2 and then 1, 2. And we print is subtree on 4, the 2 true, and this should give us false. And it gave us true instead. Did I make a mistake on the creation? So the tree that I'm trying to create is this one here. So I have a 2 that should be the leftmost, and then my 2 goes to 2 extra, as well as 3. And, oh, whoops. Right, it's because I'm using the old definition of 2. Or I'm not using the old definition of 2. To reference.
Okay.
Yeah, now we got false as I'd want.
All right. Okay. That looks good to me. Let's see. What if these were binary search trees? Would you change your approach at all?
Yeah, I think that should probably let us change how we work with this. So for the actual traversal itself, when we decide to go and find, say, the root, you know that every time that you are at some level, you have the choice of either going to the left subtree or right subtree, right? So based on the value of your root, you don't have to. If the value of your root for the smaller one is say less than what you're currently checking, then you would traverse on the left, right? And if it's greater, then you would traverse on the right. And if it's the same, then you would start your match function from that point, right? So the match section is the same. It's only the how you traverse that should change. And I think, are you guaranteed for this BST that the values are unique?
The values are So we can assume the values are unique for this BFT. Are you
Right.
thinking about performance? Is that the reason you're asking?
Well, it was more of, say we try to do a search and it fails, and it turns out that there's multiple, values that match up to what's on the root, right? So then the question becomes, do we traverse left or right, if there's multiple values? And so how would we break that, right? But if the tree is unique, then you don't have to care about that. So I'm thinking of, yeah, so if it's unique, then our match function is the same, but our traversal will change.
Okay, fair enough. What about the complexity?
Yeah, so for that, it's definitely, at worst case, it should be big O of t, where t is the larger tree. That's not true, actually. It should be each level you're going down by the height, right, on the BST, and that's your maximum traversal going downward. But then you also have your traversal that has to work with match. So really, it's big O H plus S, right? Where H is the height of the tree, and S is the size of the smaller tree. And it really depends on which one of those is larger.
Okay, H is the height of the larger tree. Okay,
Yeah,
and S is the size of the smaller tree.
yeah, and it purely depends on which one is larger. Because you might have, say, this giant tree that is, 100 in depth, right, in its height, but the smaller tree is at the very bottom of that, and it's only 3 nodes. Or alternatively, your match function may be at the, very beginning, or let's say it's near the end. Let's say it's the exact same size as the larger tree, or maybe just one item less, because I guess when it says smaller, that means strictly smaller, right? In that case, the size of the smaller tree is going to be what will balance this.
Okay, is this the worst case performance or this is the best case performance?
I think this ends up being the worst case, because what it's trying to get at is that the worst case is really split into two different cases, right? You either have that matches up almost completely. It's this, and then 4, and then your t is going to be 2 and 4, right? No, that's not a good example. Let's say it's, and this isn't a BST either. But let's say it was, and we're really just talking about the placement of the nodes, right? Here you're going to spend majority of your time looking at S, which is the set of nodes 2, 1, 4, even though your height is only 3, right? Alternatively, though, you could have 1, 2, 3, 4, 5 as your BST, and your smaller tree is only 4 and 5. And so it's really bounded by the height.
Okay, and what would be the best case performance on the tree?
I guess that there's no, to me it seems like it would be when there's no subtree that is there at all, right? Like it's a single node, potentially, is the size of your subtree, and you end up just, traversing left to right each time. And say it's a balanced tree, in that case it's going to be, log n time, right? Where n is the size of t.
Okay.
Yeah.
All right. Okay. So, so let's go ahead. Let's do another problem. Okay.
Sure.
We could leave that stuff right there. Not an issue. Okay. So, let me go ahead and start reading it. I'm going to just comment it out so it doesn't.
Okay, so what does pretty mean in this case?
Pretty means we want to print the tree in this basically structure that I have it on screen. So right. So as you can see, right, so given a tree, right, think about it that you want to print it in the way. I wouldn't worry about these slashes. Honestly, if you get it, great. If you don't, that's okay. The goal is to be able to print this structure on the result.
Okay, so is it supposed to be that I'm supposed to group together all nodes that are on the same vertical line? So let's say A is at level 0. Does that mean that B is at level -1, and then C is at level 1, and then E is also at level 0?
So, so what it really means is, so if you look up the vertical line for D, there's no other node on that line. If you look up the
Okay,
vertical line for K, there's nobody else. G, nobody else. So the goal is when you print it, or when we print it, we want to make sure there's nothing else in that line that gets that's on the tree.
I see.
Yeah.
Okay, so is there no future lines that could possibly overlap?
When you
Because
say
when I
lines,
so what if I have something here as well is and it keeps going left. Is there no point at which it would overlap with an existing character? So let's say this was just G, right? And then I have another line, uh, another value. Doesn't this overlap with some item at some point if you keep
right.
going left?
So the goal is basically that we want to space C and the subtree on this side enough. So, for example, something like this, and I'll just replace that with the original structure, but something like this, right? So we have enough space now for G not intersecting A, if that makes sense.
I see. Okay.
So
Sure.
it doesn't need to be symmetric between A and C, but the requirement is to make sure it doesn't intersect in the same line.
Sure. Okay. So just thinking about this as what it starts off with, let's say I were to break this down into a bunch of vertical lines. At the minimum, it seems like I would, in the simplest case, have to separate, a node from its left neighbor by 1, right? But depending on how many nodes are in future right subtrees in that left subtree, it might go to multiples of 1. So it goes to a distance of 2 and 3 and 4 and so on, right?
Okay, and maybe I don't follow, sorry, but so if you take an example, let's walk through, what you're suggesting.
Yeah. Uh, so is the distance between A and B here supposed to be 4, or is that?
A and B is supposed to be 4. So let me go back. So distance between, so currently A is right here, right?
Yeah.
And you see my cursor, right? Exactly. Okay. Okay, so I see what you're saying. 4 is B. I think so. Yeah. So, right. And again, like it could be 3. I don't mind. It needs to be a space. The goal is, if you look at the vertical line for B, there's nobody else. So that's my goal.
Right. Okay, so maybe one thing that I can think of is normally when you do, say, a horizontal traversal of some binary tree, you end up
Mm-hmm.
getting all of the items that are on the same level, right?
Yeah. You
Once
mean
you
like
have, sorry?
you mean like each line of the tree?
Yeah. So you end up
Mm-hmm.
finding all of the items that would, say, overlap if you were to, instead of vertically traversing, horizontally traversing, right? Like left from right.
Mm-hmm.
If you have those items, it tells you exactly where the conflicts are. And to do, a horizontal traversal, all we have to do is do any sort of traversal that we want on a binary tree and associate, a level, a horizontal level to an array inside of a
Sure.
map, right?
Sure. Mm-hmm.
So that part is uh, we can do. But once you
Yeah.
have all of the items that are within some level, what information does that really give you? So let's pretend that this was a normal BST, right, that isn't printed off. In that case, this is what our map would be. We would have 0 going to A and
Okay.
E, I believe. Yeah, because the C goes left, so it should go back to 1, right? Does it normally
So
print
why
off
is
like that?
E 0?
Because I'm saying this is that of being pre-printed, right? Um, this is the case where you end up going right by 1 for C, and then you go left by 1 for E. So I'm just going to draw this out on
I
a piece of
see. I
paper.
see. Okay. I see. Okay.
Yeah, if you have A,
From a
C,
sequence perspective, A and E kind of line up. Okay.
yeah. Um, if you were to just, increment by 1 every time you go right, and then decrement by 1 every time you go left, right? So A and E match up, and then you'll have at -1, you have, I guess, B and G.
Mm-hmm.
-2, you just have, I guess you have 2 items here. You have D and K. 1, you end up having C and H. Is that
Mm-hmm.
true? No, I guess you also have I, right? That does not make sense to me. Right, that's just because of the way that it's printed out. But yeah, the levels should match up so that at 1 you also have I. And then 2, you have F.
Mm-hmm. Mm-hmm.
3, you have J. How does this actually end up helping us out? So all of the items that the distance between A and its left and its right child should be at minimum the number of items that you have preceding A, right? Or following A. I think that's the way that we can think about this. So if we were to create this map using a level by level traversal, then we should have the guarantee that all of the items that come first in the array are at higher vertical levels than items that come later in the array, right? So A is always going to be a higher level than E, and then C is going to be a higher level than H and I. So yeah, if we want to figure out the distance that there should be between A and the very first item that comes to the that comes to the right of it, it should just be okay, but that's not really entirely obvious, right? Because what if it turns out that the item that's on the same level isn't, the left subchild of C? It might be, say, some item that comes all the way down here, where we get this followed by the exact same thing as before, right? Where you have a bunch of G's. But even if you had a bunch of G's the way that we do on line 88 and 86, the distance between A and C still increases, right? So in that case, I think it is relevant to have your distance to C increase depending on the number of elements you have following. So what I'm thinking is I start off with my root, which is A, and I know it's the first element that comes in my level 0, and the number of items that should come for the distance to its right subtree, it should end up being, like I was saying, the number of elements that come afterwards, right? Plus 1. So the distance to C, in this case, should be 2. If we're, ignoring the slashes. And so what that should let me do is fit E in this position here.
So why is C 2?
So I'm not including the slashes because you mentioned I can ignore them, right?
Okay. That's okay, but still, why? What is this G and a G in the first example? So I'm just kind of trying to see why C. Why is there a space between A and a C to begin with when you're at C? Because you don't know what's below E to even determine how much space should be left. No, I'm trying to understand.
Yeah, interesting. I don't know what's below E.
That's right. So it could be a G and a G, like in the first example, which could push C even further out.
Okay, let's.
I think we are in the right direction. I think, and I'm trying to hint you. So we are in the right direction. Just letting you know.
Right. Okay, let's see what happens with the the two G's that I have from above. So if I were to have those, my H goes to level 1 again, and then my first G is at level 0, and then I have a second G at level -1, right? But the way this tree is drawn out, this -1 G level is still in front of my A, right? When really, what I'm imagining is that it's out here instead, to the left of A. I'm not really sure how to account for those based on what I have so far.
So let's say if you could flatten this tree in something like this, right? Does that help? Let's say what is it? B, G, A. So let's pick the second tree, right? So that there's no confusion. P, A, E, C, H, E, H, C, I, F, J. Does that make sense?
That is the second tree, right? D,
Yep.
K, G. Yeah, that's just the the order, right? The horizontal traversal.
So if we know that, do you think we can solve the problem?
Yeah, okay, let's think about how you're actually spacing these out in that case. I guess this ends up just being.
Yeah, let's not worry about how we got the string. Do you think we can? If we know that this is the string, do you think we can build that tree?
Yeah, I'm trying to like in this exact form, because from this it seems like the answer would be no, right? Because I don't even know what the root is in a sense.
We have the tree, right? So we still know the tree.
Oh, I see. And the elements are unique. Okay, if that were the case, then
let's assume the elements are unique, right?
Yeah, if that were the case, then I should be able to. Let's see. I would first go searching for the A, right? And I know that that's my root. Everything to the left is going to be the left child. Everything to the right is the right child. How would I be able to figure out which item exactly is the right child? I already know what it is by just traversing the tree. So I would see that the C is the right child, right? So the distance between my A and C should end up equaling the distance between, the items in the actual string, right? So here it ends up being 3.
Okay.
Yeah. So I would want to make sure that to my right child, or to the element C, it's printed 1 level below and 3 to the right, right? And then when I check the E, it's printed 2 to the left of C, and all I have left is the H, which I know it's only 1 away.
Okay.
So that I think ends up being the general way in which I'd go in and print things out, right? And what I'd do is I would look at what my left and right values are at each node, and I would search for the distance in the string. And I would
Okay.
pretty much print one level below and to that distance for every item. I should, be able to just do any sort of traversal, or at least as long as I process the root first, some sort of traversal.
Okay. All right. Fair
Um,
enough. And can we build that string that's the string that we built? So DKGB. How do we build the string?
it almost seems like it's the exact same as what I'd get from doing the level by level traversal. So if I remove this, the extra G's, I end up with DKG, I end up with BG instead of the GB. So let's do the comparison. So I have DK. If I were to just go ahead and, so it is still the horizontal traversal, but it shouldn't necessarily be a level by level traversal. I think if I were to do this as a in order traversal, how does that change things? So I have, DK is definitely matching with the in order. G matches B, A, E. After E should be H, H. So yeah, this seems like it's just the in order traversal of the tree, if I were to
That
look
is,
at it.
yeah.
And that should
That's,
match up with, uh, what the in order gives us, right? It lets us process all the left first, followed by the root, followed by the right. So given these two things, I guess the full solution approach should end up being that we perform an in order traversal in order to retrieve this string. And then once we have the string, we can just do the, the starting from the root search for the item. And is it always just going to be, so I talked about processing the nodes in order, but do we just, I guess we already know what their, position are going to be horizontally, right? The only thing we actually look at is what their position is going to be in terms of the level. So we can actually save a bit of time, and instead of having to bother with doing that other complicated traversal, if we were to also store the level of the items while we're doing the in-order traversal, we should be able to just use that info, right?
okay.
Yeah.
That's fine.
So
Yeah, I mean, that's fine. What you're suggesting is like hold a different data structure. So yeah, what would be the data structure we'd hold that information in?
if you just hold it in a sort of what is it, set, right? We should be good to go or not a set, a map pointing to a set, or a map pointing to a level. So it should be a map pointing the character to an integer, so that what we're doing is as we go through, we start from D, we just look it up to determine its vertical level, and we already have its horizontal level based on its placement in the array, right?
So that's interesting. So we would store the character to the level of that character. Is that right?
Yeah, yeah.
So so when we print it, how would you print it? So you will always start at D or would you start at A?
We could just start at D for this and make it so that instead of bothering with printing from the root, if you just had some n by m array or matrix, you should be able to
Mm-hmm.
place in all of the letters to their correct position in the matrix, right?
I see. I see. But let's assume this is like the standard print buffers, right, that we have from operating system. Do you think we can still do that?
By print buffer, do you mean some of the, you
Like
can't
since,
allocate all of
you
the
know,
space?
well, probably you could. So you use the, let's say using
Oh,
Python, using
but
just the
line by
print.
line, right?
Yeah,
Yeah,
line by line.
yeah. Yeah,
So,
this wouldn't work out in that case.
so could you
Um,
could you change your data structure in a way that it could work for line by line?
uh, yeah, I guess if that were the case, if you were to store all of the, this is the thing from before where you were to store the vertical level to a set. If you were to do that, then you should be able to just go through, starting from the 0th level up to the nth level and
Mm-hmm.
find their position, right,
Okay.
inside the string. But there we'd have to do a long search through the string, right? Which is a big O of n time operation where n is the number of nodes.
Mm-hmm. Mm-hmm. Okay, and I think what you mean is like store the levels to the list of letters, right? I just want to make sure.
Yeah. Yeah.
Yeah, okay. So it won't be a set because otherwise you lose the ordering.
Oh, okay. I wasn't suggesting that we just. I was going to suggest that. What is
You
it?
mean a list,
The
right?
ordering stuff. I meant either because I didn't consider ordering this. The only thing
Oh,
I was
okay.
considering is that they're on the same level.
I see. I see. I
Yeah.
see.
'Cause even if we use the
Uh,
list, the ordering doesn't
you,
really help us without going through the string afterwards, right?
um, uh, right. So, yeah, I think the goal is to make sure we are able to print that tree in the way it was originally given. So that's what we lose. The information that we lose is the placement of the numbers. So if there's a, let's say there's a, this is not a full binary tree. So I think, you know, what you're suggesting is like put the element, and if it's blank, put like an empty value there. So, but in that order, right? So it would be a list of values that you put in order. So when you print them, they come back in the same order that it was put in. Is
Right.
that's what you're suggesting, right? So let's say there's a D E F is the third row. What we're basically printing is D, and then blank space out there because there's nothing below uh, B on the other side, so it would be a blank. And on this side of the tree, it's going to be E and a F. But if there's anything else, it would be a blank space as well.
Yeah, you would get that just from the string itself, right? Like between D and the E, there's a bunch of other characters that aren't on that level, right? So those would all be blanks for each of the characters that are not on that level. I think
Right.
it's
So
probably simplest through, I guess through code, because I think we're thinking of about the same thing. Uh, is it okay if I code this
yeah,
out? Okay.
Uh, it's uh, that's okay. We don't have to code it out because it's 3:51. Sorry, I have a hard stop at 4, so I have to run, and probably want to end up like 2-3 minutes earlier, so I can put
Right.
in some notes in. But yeah, no, I mean, go ahead after the exercise if you prefer to code it out. That's fine. But yeah, that's
Right.
kind of the approach. And one of the follow-up questions I would probably ask. Is how could we make this tree work for duplicates as well? So if the BST has duplicates, how could we make that work as well? So um, just putting it out in the open, something to churn on. Um, but yeah, this is fair. I mean, I think we got to the right approach. What is, in order traversal and getting to that place where we could be able to build the tree out. I think printing is the easier part of the whole exercise, right? So
Right.
we should be able to get that through it. Awesome. Did you have any questions for me?